Today we have Choi Daebeom from the University of Pennsylvania and give you us an introduction to Anabelian geometry.
Thank you very much for the introduction. Okay, so today I will talk a little bit about Anabelian geometry, about what it is and what is the important theorems and conjectures in this area. And when someone starts talking about Anabelian geometry, the first thing that one might talk about is mostly like got a group of certain interesting fields and some valuations and so on and so on. But today I will take a different route, which is approach to the Anabelian geometry through some more topological geometric way in terms of surface boundaries and mapping class groups. Okay, let me start. Okay. So first, I will talk a little bit about the general fiber boundaries. A fiber boundary is a morphism from the total space G to the base space B, where each of the fiber has the same shape F, and of course you have these local trivialization conditions, like the ones for vector boundaries. And the idea is that this is some kind of an axiom that I will assume for the whole talk, study of fiber boundaries. Useful for understanding both the base space and the fibers. That is something that I will not explain and just assume that everyone agrees with this. And moreover, I will assume that here F, E, B are just topological spaces. However, I will assume that all of them are good. I will not talk about like Hawaiian earrings or like like rational numbers or something like that. These are all good spaces. Okay. So there are several ways of studying fiber boundaries. For example, like we have such important tools such as the exact sequence for the homotopy groups, like these. And we also have some kind of spectral sequence. For the fiber boundaries, but like I will not use them in my talk, but I want to mention a little bit about them because like I will use some kind of analogous lizards which resembles this kind of things. Okay, so for example, like, okay, let me give you several examples of the fiber boundaries to begin with, because like, this is not a trimester about low-dimensional topology or geometry. So, okay, so what is an example of fiber boundaries that you are familiar with? Sorry? Tangent boundaries. These are examples of vector boundaries. So vector boundaries is when you have your fiber has a vector space structure. And also there are some more easier examples. It might not be easier, but similarly interesting examples, such as when F is just a set with discrete topology. If F is a discrete topology, then fiber boundary exactly corresponds to something called the covering spaces, and this theory of studying fiber boundaries are somewhat equivalent to study of the fundamental group of the base space. And however, these the boundaries that we are considering in this talk are a little bit different from these, because we are mostly focused on the case when F is SG, here in this talk, SG always means a complex orientable surface of genus G. Yeah, but some of the things that I will talk about right now, we apply for much more general fibers. Okay, so let me give you some examples. This example is when E is equal to S1. So just a circle. So how can you construct a bundle over a circle? There could be several ways, but one of the most easiest way is that the circle is nothing but a closed interval quotient out by the relation that 0 is equal to 1. So what you can do is that you can just take an interval, this is between 0 to 1, and take the constant bundle f times the closed interval, and you identify the fiber at 0 with fiber at 1. And to identify these two fibers, you need a homeomorphism between f to itself to identify these two fibers. So you need a homeomorphism f, which is inside this group. So if you have such f, then you can define the fiber bundle as the following. This is just quotient of this trivial bundle over the closed interval by the relation that 0, x is equal to 1, f over x. Then this defines a natural fiber bundle over the circle. And this is usually called the mapping torus. You might have heard about this construction because this is shown in, say, Hatcher, so that kind of algebraic topology groups. And also, this is very interesting, very important to construct some three manifold or something like that. Okay, so here is our first interesting theorem. So if you have an element in the homeomorphism group of F, then by associating the mapping torus using F, you can construct a F bundle over S1. Then an interesting fact is that this is indeed surjective. It is not extremely hard to see because to prove this, we will use this natural quotient map from the closed interval to circle, and you pull back the fiber bundle. Then it is not very hard to prove that if F is good, then any F bundle over the closed interval is just a trivial bundle. And the only way to make that into S1 bundle is the mapping torus construction. So this, if F is good, then this is the only way to make the fiber bundle over S1. And the second interesting fact is this. We have two different mapping torus given by homomorphisms F and G. And we can ask when they are equivalent to each other. The answer is that they are equivalent to each other if and only F and G are in the same component, connected component. So if you consider the homomorphism group of F, then F has a natural topology given by the compact open topology. And if F is good, then it is a good topology on the homomorphism group. And especially if F is sufficiently good, I will not talk about what is the exact definition of sufficiently good. But if F is sufficiently good, then this group is indeed locally path connected. So any connected component is equal to path component. And if you think about this, if f and g are just different in the same path component, for example, like homomorphism group of f might have several different components. However, if f and g are in the same component, then since I mentioned that the components and path components are equal to each other, there is a path connecting f to g. And you can twist this construction a little bit everywhere by twisting by this set of homomorphisms, this path of homomorphisms. Then you can obtain the isomorphism between these two. And basically, the converse is more or less the same. If they are in the different path component, then you cannot really continuously evolving f to g by a path. So this is an if and only if condition. So what this theorem is talking about is that we basically know what is the f wonders over S1, and as a conclusion, you say that like f wonders over S1 is basically the path component of the homomorphism group. Okay.
Can you give some examples of f that are like reasonable but not good?
Sorry?
Can you give some examples of f that are like reasonable but not good?
Honestly, I don't know. But
So anything that I can
don't
think
know.
of
Maybe
is good.
if f is the topological space of p-adding numbers, then I don't really expect it is good.
I don't know if that's reasonable.
Yeah. Okay. So any other questions? Okay. So this leads to our natural definition. The mapping class group, which is a word containing the abstract of f, is defined by. There are several notations for mapping class group. I will just say MCG of f, because this is mapping class group. However, sometimes people use the notation mode of f, especially when f is the genus orientable surface. This is some notation that topologists usually use. This is just this one, pi 0 of homomorphism group of f. And you can consider this as if f is sufficiently good again. This is homomorphisms of f up to isotope. If that means something for you. So this example says that mapping class group is very important to study the wonders, and at the very least, it tells you, it gives you a complete classification of wonders over S1, the third. Okay. Any questions?
So what is mode f is same as mapping class?
Oh yeah. I mean, this is just another notation.
Oh, okay.
Yeah, but sometimes this is usually used by low-dimensional topologists or geometric group theorists, especially when f is like some surface. Okay. Okay, so that is for S1. So now we will talk about like general basis. Oh, maybe before that, it would make sense to at least give you one example of the mapping class group. If you consider the mapping class group of torus, can someone guess what is the mapping class group of torus? There is like one very obvious candidate. Sorry?
The direct sum of the or
0 to z.
Yes. Yeah, it depends on whether you want orientable mapping classes or you don't care about the orientation, but since we are not caring about the orientation, this is here too. Yeah, they define obvious automorphisms of T2, and we can prove that these are indeed the representatives of each connected components. But like I want to mention that many people, I mean, there are several subtleties between regarding the word mapping class group. The mapping class group used by algebraic geometers are different from mapping class groups of topologists, and like people sometimes add orientations, sometimes do not care about the orientations. And I think in topology, people usually care about the orientations, and they call this extended mapping class group or something like that. That is what I will talk about. That the extended mapping class groups are something that I will talk about. Okay. Oh, maybe I will. Okay. Maybe I will just give you one more theorem about the mapping class group. The mapping class group of a surface is nothing but the outer automorphism group of the fundamental group of the surface. This is called Penn, Nielsen, Bayer theorem. So if you let G is equal to 1, then the fundamental group is G2, so outer automorphism group is equal to just the automorphism group, so that is GL2G. And in general, this is equal to the outer automorphism group of this. And this is like finitely generated, finitely presented, and there are a full body of work of topologists regarding these mapping class groups. This is very interesting area. Okay, let me explain the general base case. What can we do for general basis? Where there is indeed one thing that we can do, there is one obvious thing that we can do. We know everything about what is everything about the F wonders over S1. It corresponds to the mapping class group. So you can take any map from S1 to B and take the pullback. Then since any F wonders over S1 is a mapping torus, this should become a mapping torus of some element F in the mapping class group. So if you have, we can associate if you have a map from S1 to B, then this goes to mapping class group of F by this association. And it is not extremely hard to prove that this map is invariant under homotopy. So in particular, this defines a map from pi 1 of B to mapping class group of And I will call this monodromy representation. Where, again, there are several different notions for definitions for monodromy representations, because like sometimes people consider the representations of pi 1 on various homology groups on F, and they call them monodromy representations, but in this talk I will call these the monodromy representation, because basically everything comes out of that. Okay, let me give you an example. In this spectral sequence that I've written down here, if you consider this homology group, this is like a little bit, like there are a little bit subtleties in here, because although I write down Hj of F, it is not just a group. It is not a group, and it is indeed a local system. And you should take the cohomology of these in terms of a local system. Here, local system just means a representation of the fundamental group. So, to even define what this spectral sequence is, you need a representation of the fundamental group on this J's cohomology of F for any J. And indeed, it comes from here. Because, mapping class group is basically the pi j of the homomorphism groups. And if you have a homomorphism group, homomorphism of F to itself, then it obviously acts on Hj of F. And this action is homotopy invariant. So there exists a map from the mapping class group of F to automorphism group of any degree cohomology. So basically, if you compose this map with monodromy representation, then this will give you a representation of the fundamental group of B to the J's cohomology group of F. And this is also a very important object. If you're familiar with the notion of sheaves and local systems and something like that, then this is nothing but just the higher push forwards. And we have some mortars to study these kind of things. So sometimes this is called the monodromy representations. Anyway, what I'm saying is that by pulling back everything to S1, we can get a representation of fundamental, strictly speaking, not a representation, but a homomorphism from the fundamental group to the mapping class group of the fiber. And it induces lots of representations on homology groups, or basically any homotopy invariants. So this is, in some sense, the universal monodromy representations. So, any question so far? Okay, so the finite tree, this is a very important invariant. I mean, the monodromy representation is a very important invariant of a fiber wonder. That part is very clear. However, the question is that to what extent it is a good invariant, or in the other words, to what extent it determines the fiber wonder. The answer is somewhat surprising, at least to me. The theorem is that, as in the case of S1, this monodromy representation is a complete invariant of the fiber wonder. It just determines the fiber wonder when F is the surface. I mean, the compact orientable surface. In this case, there exists a one-to-one correspondence between SG wonders over any good basis and homomorphism from pi1 of B to the mapping class groups of S. So the SG boundaries, which is a very geometric or topological object, is completely determined by a very algebraic object, which is a monodromy representation, which is quite a surprising theorem. Any questions? Yeah, I think okay, so, sorry. Let me make it clear. Which says something. Okay, I will not give a full proof of this because this is not a topology geometry talk, but I will give you a hint of how to prove this. The most important technical result in this proof is that a theorem of Hamstrom. It states that if you consider the connected component of the homeomorphism group of SG, then it is contractible. Oh, again, G is greater or equal to 2. This is not true if G is equal to 1. Okay, so how can we prove this theorem using Hausdorff's theorem? Where there are several ways, like I represent basically 2 equivalent proofs. First one is doing the transition maps. Where basically, by the definition of the fiber wonder is nothing but the data of a bunch of transition maps which satisfies cocyclic conditions, which means that there are fiber wonders. This is equivalent to this U is just a open cover of B. If you are willing to assume that B is super good, then like you may assume that like every UIs and every finite intersections are contractible or something like that. But in general, you don't really have to. Anyway, fiber wonders are given by like bunch of such transition maps which satisfies the cocyclic condition. So basically the idea is this. The target of this map is homomorphism group of F. And we want to sharing this homomorphism group to mapping class groups. However, the difference is contractible by this theorem. That is basically the heart of the proof. So there are one more elementary way of doing this. Like, you can pass it to mapping class groups, and so define a cocycle which defines the homomorphisms here. And you can prove that that is one-to-one by using contractibility of this, kind of a standard argument. If you are willing to use a little bit more high-tech algebraic topology, I mean, high-tech for me, not genuine algebraic topologist, you can do the following argument. Like, basically, SG wonders over B is classified by, there are too many bits. This homotopy class of this map. This homomorphism group of SG is just a topological group, and you can consider the classifying space. Then the SG wonders over B is classified by the homotopy class of this map, and which is not very. I mean, if this is first time seeing this, then it might be very strong theorem, and it is a strong theorem, but it is not very surprising because it is more or less a different way of presenting this. If you unpack the definition of the classifying space of the homomorphism group of this. And since the mapping class group is a quotient of the homomorphism group, you can pass it to the MCG of SC. And what is a corner? Corner is the connected component of the identity of the homomorphism group, which is contractible. So, at the end of the day, you know that this is a homotopy equivalence. And this is classified by homomorphisms like this because MCG is a discrete group. And like, just the first proof and second proof is not really different proof. They are like philosophically the same, but like it depends on whether you prefer elementary way of doing this or like some more conceptual way of doing this. Any questions? Okay, since this is end of the topology part of my talk, I will wait for 50 seconds of awkward silence for more questions. Okay, before I jump into an actual Anabelian geometry, let me remark one thing. There is a moduli theoretic interpretation. So here we will think about complex, like say complex analytic category. In complex analytic category, the analogues, the energy of the surface boundary is just a map e to the b, which is both a complex manifold or complex analytic space or anything that you want, which is like, proper, smooth, related dimension 1, and fibers are genus G. And we have another way of describing this. Such map corresponds to a map from B to the moduli space of curves MG. Then what can we do is that with this map, you can associate the map between pi 1s of each side. And you know what? This is indeed the mapping class group of S. Honestly, I'm lying a little bit. The difference is that this should be the orientable mapping class group of SG, but yeah.
So you're just mapping I guess the map from B to MG is just the fiber. It just picks out the fiber, or what are you?
Yeah, send every point to its.
So whatever the fiber is. Is it up to isomorphism or anything, or?
Sorry, up to isomorphism.
If you have like well, yeah, I guess if they're like isomorphic bundles, do they get mapped to the same?
Oh yeah.
Oh, okay.
Yeah. So this is the monodromy representation that we described above. I just want to mention that there is a relation between the moduli space of curves and these mapping class groups. And oriented mapping class groups are indeed just the fundamental group of moduli space of curves. Okay. Now, let's change our gear and talk about the linear arithmetic geometry. I mean, not arithmetic geometry over linear numbers, just genuine arithmetic geometry. Here, what is a genus G surface? Basically, genus G surface is an arithmetic curve of projective, smooth, and genus G. There is a classical analogy between these arithmetic curves of genus G and compact Riemann surfaces. They have lots in common. For example, genus is well defined in both sides, and like many important theorems, such as like Riemann-Loch theorems or Horwitz theorems. Yeah, it's such kind of theorems in both categories. If you don't believe me, check Hausdorff chapter 4. Although it assumes that the base field is algebraically closed, most of the things also holds for any field. Yeah, but however, like people notice that this is not a perfect analogy. The problem is lying on here, the base space. Expect K. In terms of Zariski topology, this is a point. Because there is a point, and although the shift of functions are a little bit different, but like this is just a point and there is no interesting topology that happens in here. However, if you consider the entire topology, this is defined in another point, if K is not separately closed. Because there are lots of interesting covers of K in terms of the Galois theory, which is very far away from trivial. So the problem is that the base is not really a point. So there is a difference between X and compact Riemann surfaces. For example, if you compute the étale cohomology, the étale cohomology of this is much more complicated than the étale cohomology of the compact Riemann surface if K is not arbitrarily closed. So the point is that this classical analogy is only good, or maybe this is too strong, only perfect if K is arbitrarily closed or separately closed. It doesn't really matter in this talk. Okay, so kind of more modern analogy, modern or kind of a better analogy is this. We have this X over step of K. Then we can take. Then we know that we agree that spectrum of the arbitrarily closed field is a point also in étale topology. So we can take the fiber by pulling back it into the point. Then what is the fiber? Fiber is xk bar, which is kind of analogous to compact Riemann surface by this classical analogy, and which is analogous to just the genus G surface. Okay, so the punchline is an algebraic curve, proper smooth algebraic curve over a field is a surface function. Over spectrum of K, whose fiber is xk bar. That might be a better analogy that I'm referring to. Okay, this is not directly related to what I will talk about, but one very good example is when K is a finite field. Okay, this sounds stupid when you first see this, but it is not really very stupid. If you take the spectrum of a finite field, then it more or less looks like a circle. Why? Because if you consider the fundamental group of S1, then you know this is just integers. I did not talk about what is the fundamental group of a field, but that is nothing but the Gauss group, which is not integers, but something looks like an integers, which is generated by the Frobenius automorphisms. And we can talk about the higher homotopy group. Higher homotopy group of circle is 0 if I is bigger than 1. And we also define higher homotopy group of a finite field, although I will not define it, but anyway, this is also 0. Indeed, the second line also holds for any field. For any field, higher homotopy group is 0. So, like, spectrum of FQ is someone like S1. So, what is this? Curve over FQ. It's someone like SG bundles over S1, which is something that we have studied, and also which is a three manifold. So this is the analogy between curves over finite fields and some three manifolds, and this usually goes with the name of famous Nansen primes or arithmetic topology. So I'm just mentioning that this looks like a very crude analogy, but there are lots of which is a very serious analogy, and there are lots of body of works which devoted to this analogy. Okay. So what we will do is we will study algebraic curves over a general field using that analogy. However, I did not really define what a pi1 here. Pi1 is here. So I will first define what a pi1 is in the sense of algebraic geometry. Any questions?
Is this triviality of the pi i's for greater i's of a field Hilbert theorem 90 in this?
No.
Okay.
That corresponds to the étale cohomology of K is equal to the group cohomology of the Galois group. So spec K is in some sense K pi 1. So
Yeah, but why are all these pi i's equal to 0 for I greater than 1?
sorry?
You mentioned these pi I mean, you didn't define them anyway, so. But
Yeah. So okay. So basically, I think your question is that why higher homotopy group of a field is trivial.
yeah.
So basically, the reason is that you can prove that the étale cohomology of certain shapes over a field is equal to the group cohomology of the absolute Galois group. In topological sense, it means that a cohomology of a topological space is equal to group cohomology of its fundamental group, which holds if B is K pi 1 space, which is exactly the topological spaces with vanishing higher homotopy groups. So that fact, higher homotopy group vanishes, corresponds to the fact that the étale cohomology of spec K is equal to the group cohomology of the Galois group. Okay. So we need to talk about étale fundamental groups. So I will not define this, but I want to state some facts. Number 0, pi 1 étale is a functor from geometrically pointed schemes. Here, geometrically pointed means that this point is not just a topological point, it is a geometric point, which means a morphism from a algebraic closed field to this scheme to profinite category profinite group. If you're not familiar with profinite groups, then it's okay. You just consider it as a group. It does not play a significant role. And I mean, in this talk, And first, definition is similar to topological pi, which means that to define this functor, we take the set of what is a covering spaces, and as in topological fundamental group, we define this fundamental group as some automorphism group of systems of covering spaces. That is what I'm saying here. And second, pi 1, étale pi 1 of field is GK, absolute Galois, which is not very surprising. And third, if K is an arbitrarily closed field which is naturally embedded in C, and X over K is a variety, then étale fundamental group of X is equal to étale fundamental group, just the topological fundamental group of corresponding complex manifold, and take the profinite completion. Again, if you're not familiar with profinite groups, then just think that they are the same. So this is basically saying that if your field is characteristic 0, then the étale characteristic 0 algebraically closed, then the étale fundamental group is not very different from the topological fundamental groups. And finally, we have, thanks to this, we kind of understand what is the fundamental group over algebraically closed field of characteristic 0. This theorem tells you more generally there exists an exact sequence which decomposes the étale fundamental group of X into a geometric part, which is fundamental group of the base change and also Galois group. So this is decomposed, this group, which is sometimes called arithmetic fundamental group, is decomposed into two parts. First part, étale fundamental group over X K bar governs the geometry over X, and GK, which governs the arithmetic part, because it is a Galois group over field. Okay, so we have fundamental group, but we don't have a monodromy representation yet. And one thing that we want to note is that monodromy representation is morphism from pi 1 of B to the Matrix group of F or SG. which is equal to outer automorphism group of pi 1 over c. And one proposition is that if you have an exact sequence of groups, this is just an exact sequence of groups, then this naturally induces a morphism from H to the outer automorphism group of M. Why? Because if you have an element in H, then you can take a lift of that element to G and take the conjugation action on N. This is not well defined because the action that the action of the lifting defines your choice of the lifting. However, these actions only differ by conjugation by N. Because if you have a lifting, then all other liftings is of form G times N. So all of them differ by a conjugation by N. So if you could take the outer automorphism group of a group, then this is where this representation is well defined. And if we apply this proposition to forms, then we get a representation of the K outer automorphism group of pi 1 étale of xk1. Which looks kind of familiar, right? Because what is GK? GK is the fundamental group of the base, which is spectrum of a field. And xk bar is a fiber. So this is outer automorphism group of the fundamental group of a fiber. So this is exactly analogous to the monodromy representation in topological category. So this is basically algebraic geometry analog of the monodromy representation. So I will also call this a monodromy representation. Any questions so far? Okay. So the obvious question is that in topological category, we learned that any fiber boundary is determined by a monodromy. Any surface boundary is determined by its monodromy representation, right? So we can basically ask the same question, which is asked by Gauss-Hendrik. The monodromy representation determines X. But this is trivially first, because if K is algebraically closed, then there are lots of different algebraic curves, but the monodromy representations are trivial. So you need to assume that assume some condition on K. I will just denote that for arithmetically interesting K. This is the question of Gauss-Hendrik, and sometimes referred to Gauss-Hendrik's Anabelian conjecture. Now we have an answer of this question for many cases. The answer is yes. For K, either a finitely generated field or a p-adding number field. And there are some more fields where this works, but I will not talk about this. So basically, all the finitely generated field or p-adding number fields, this is true. And there are many people involved in the proof of this theorem. There was a line of proof which leads to proof of this theorem, which is proved in the late 19th to early 2000. So I will name 5 of them. First, Nakamura consider some earlier cases of this conjecture for genus 0. I mean genus 0 with some punctures. And Florian Papp, who proved a birational version of this conjecture. And Tamagawa, who considered the case when K is finite field, and his approach is basically the basic serves as a basis of the proof of the equal conjecture. And most importantly, Mochizuki, who proved this theorem for characteristic zero, and Jakob Sticks, who proved this theorem for positive characteristic. Any question?
So in this question, k is fixed, and you're only.
That is a good question. Yeah, here k is fixed. However, there are other questions. There are analogous questions for what happens if we vary k, and there are some positive answers and some open questions. Especially, this is usually called isom version of the Anabelian conjecture because it only considers about isomorphisms. However, there is a version of this conjecture which is dealing with the homomorphisms between two algebraic curves, and that is partially proof for Mochizuki, which basically, and Mochizuki's work is about fixing a field. If you fix a field, then home conjecture is also true. However, if you are trying to vary the field, then I think it is still an open conjecture. Even for Noikuri Uchida, it is an open conjecture. Any other question?
What do we know about local fields of positive characteristic?
That is a good question. I will check. Yeah, it is maybe done, maybe not. I'm not sure. I will check. Okay, so I have 5 minutes, so I will talk a little bit about the second conjecture, which is another important problem in Anabelian geometry. So basically the question is this: this monodromy representation is an outer representation. Outer representation means that like this is not a genuine, this does not act as a genuine automorphism, but acts as an outer automorphism. So the question is that hello. When can we lift this automorphism to a genuine automorphism? When this is possible? I have talked about a little bit about modular theoretic description of the mapping class groups, which is useful to approach that question because basically an algebraic curve corresponds to such a map. And if you take pi 1, this corresponds to Galois group, and the outer automorphism group of pi 1, the power of x k bar. What happens if we take mg1, which is or I would just say the universal curve over modular space? This means that like on every point on this modular space corresponds to an algebraic curve.
What's x? Sorry. In
Sorry.
the outer automorphism, what's the x?
Oh, sorry. Okay, this is a point, so it corresponds to some
That's the
point
x.
in here, and this x is the fiber of this. Yeah. So this is a universal curve. And if you take the fundamental group of this universal curve, then this is the automorphism group of pi1 and tar of xq. So basically asking whether this leads to this is same as asking whether there is a pi1 obstruction of lifting this map to this. So this leads to the following conjecture. This is possible if and only if xk is non-empty. Because this is non-empty if and only if you can lift this map to universal curve. And this is called weak section conjecture. There is also strong section or just section conjecture, which is follows from the following description of section. Okay, assume that you have a k-rational point of this curve. K-rational point of this curve corresponds to a section of this structure map of X as a k-scheme. So if you have such a structure map, then it defines a section of this surjection. So the object here is that if you have a set of rational points, then by this construction, this corresponds to this map to the section of the map from the arithmetic fundamental group to the varieties. However, this is not well defined because I am suppressing it in the notation, but there is a problem on choice of the geometric point because pi1 is well defined only when we fix the geometric point. So there is a subtlety of choosing the section. So we need to take portion of this set of sections by the action of the geometric part of the fundamental group. So considering this, there is a stronger version which is called section conjecture. Which asserts that this is a variety.
For this, you have to assume G is at least 2.
Oh, sorry, I'm assuming that G is at least 2 everywhere.
Oh.
Yeah, sorry for that. Yeah, I'm assuming that G is greater or equal to 2. We can do some, we can allow G equal to 0 or 1 if we allow some punctures or marked points, but I am not talking about this right now. Yeah, I am focusing on the projected cases of the Anabelian geometry. Yeah. Any other questions? Okay, I want to emphasize that this is Grothendieck's original motivation for the Anabelian geometry. After Fartings proved the model conjecture, Grothendieck sent a letter to Fartings basically saying that, hey, your proof looks not very good. Maybe this is a better proof. If you can prove the section conjecture, then the model conjecture reduces to prove that this set is finite. And I want to note that this is still open. This is still wide open. So, okay, let me see. Unfortunately, unlike that theorem, there is no proof of section conjecture, and I think it is safe to say this is wide open. I can summarize several results of this. This map, I would say, denote this by kappa. Kappa is injective, which is proved by Grothendieck himself. And it is not a very hard corollary of. Okay, I realize that I did not choose what is the base field, so I'll just say that K is either a finitely generated field or P of number. So for this kind of fields, we know that kappa is injective. So the only problem is surjectivity. And if you show that this is finite, then you get another proof of the model conjecture. And mixed section conjecture, which is stated in here, and this section conjecture are indeed equivalent. And this is proved by limit argument. This is something called limit argument. And there is a birational version of this section conjecture, which I will not describe in detail. But we have some more results in birational case. The p-adic birational section conjecture is true. And this is proved using the model theory of p-adically closed field by Johann Kennison. Sorry, did I write his name correctly?
Yes.
Yes, okay, good. And there is a recent work which is devoted to something called P birational section conjecture over number field. Which again, I will not assume what this is, but for this you assume more restriction on these sections. This is also true. This is proved by Bresciani. And then, very recently, like just a month ago, Florian Papp announced a preprint which says that this holds for much more general field. And okay, and for p-adic section conjectures, there are some more results. For example, if you have a p-adic section, then this implies existence of corresponding. It would be great if I say rational point, but unfortunately that is open, and we can only associate a valuation on the function field in some sense. This is proved by Papp and Sticks. That is, there are some more works, but that is my summary of some of the progress on this section conjecture. Okay, I think I'm already over time, and I explained everything that I want to explain, so that's it. Thank you for listening.